In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about observational signatures of pseudo axion resonances, transient geometry, and axion graviton conversion in the string theoretic cosmology. It was written by Andrea Patsuku from the FAST Foundation, the CNFL, USA. We propose a novel observational strategy for the detection of pseudo-axions emerging as transient resonances tied explicitly to the evolution of internal geometry in string theory and brane-world cosmologies, building upon our previous work identifying pseudo-axions as resulting from the topologically transient cycles, pseudocycles revealed by persistent homology. We detail how cosmological expansion and geometric flattering in compactified extra dimensions dynamically modulated pseudo-axion parameters. These modulations trigger resonance phenomena distinct from the standard axion scenarios such as enhanced axion graviton conversion and observable gravitational wave polarization asymmetries. We explicitly describe how geometric transitions within Calabi-Yau manifolds and D-brane configurations determine these resonance conditions. Finally, we discuss the clear, experimentally distinguishable signatures these transient pseudo-axions produce, focusing on gravitational wave observations and outline observational tests within current and future gravitational wave detectors. Now I want to talk about introduction. The Hubble constant, or as a H0 tension, remains one of the most significant discrepancies confronting modern cosmology, arising from incompatible measurements derived from local observations and cosmological inference based on the cosmic microwaves background, or CMB. While local observations such as type A supernova calibrated via Cepheid variables consistently yields values around H0 or Hubble constant, which is actually equal to 74 kilometer per second. M P per se cosmological inferences from the Planck satellite and a standard ACDM model predict that the Hubble constant is about 67 km per second MP per C. This persistent and significant disagreement exceeding 4 sigma suggests that potential shortcomings in our current cosmological framework or the existence of new physics beyond the standard model of cosmology. Motivated by these considerations, we introduced the concept of pseudo-axions, novel pseudo-scalar field closely related to standard axions but fundamentally distinct due to their dynamic geometric origin. Axions first proposed to solve the strong CP problem in quantum chorodynamics, or QCD, have also been extensively studied as potential dark matter candidates. However, pseudo-axions differ notably by emerging from transient geometric structures, pseudocycles within Calabi-Yau manifolds, and varying configurations inherent in string theory and higher dimensional cosmological models, which come from references 9 and 10. In our earlier work, in reference 3, we demonstrated that the pseudo-axions originally naturally from topological features that are robust only temporarily as revealed through persistent homology. Specifically, pseudo-axions are associated with cycles that vanishes as the internal geometry dynamically flattens due to cosmological expansions, a mechanism fundamentally tied to the evolution of the underlying compactification structure. The pseudo axion field IX thus acquires time-dependent mass and coupling parameters whose evolution is directly dictated by geometric changes between the Calabi-Yau manifold and D-brane configurations. Mathematically, the dynamics of pseudo-axion field in cosmological background can be modeled by an effective action of the form of the S pseudo-axions is equal to integral the fourth derivative of x and square root minus g the brackets minus 1 divided by 2 the delta micro r multiplied by delta to the power of micro r minus 1 divided by 2 m to m r to the power of 2 t r to the power of 2 plus alpha t divided by 4 r a micro nu rho sigma r prime to the power of micro nu rho sigma, where the mass MIT and the coupling constant alpha t explicitly depend on the scale factor of the universe IT and parameters defining the geometry of the internal dimensions. Such an action implies that the pseudo-axion field undergoes resonance phenomena when the effective mass of the pseudo-axion coincides with other mass scales present in the cosmological environment, notably the plasma frequency of the photons or effective graviton masses induced by background fields. The emergence of pseudo-axions thus provides a natural explanation for the observed discrepancies in cosmological parameters. In particular, resonance transitions induced by pseudo-axions alter the propagation and polarization characteristics of gravitational wave and photons in the early universe, leading to the modifications in observables such as the gravitational wave spectrum and photon dispersion relations. These modifications can shift inferred cosmological parameters, including the Hubble constant, thereby providing a potential resolution to the Hubble tension. In this paper, we provide a comprehensive description of the observational signatures of pseudo-axions, emphasizing their unique geometric origin and associated phenomenology. We detail how these signatures manifest observationally and outline strategies for detections through current and future gravitational wave experiments, such as a LIGO Virgo LISA telescope and pulsar timing arrays, string theoretics, cosmological axioms, resonances, and Matthew dynamics chapter. Axions in string theory naturally emerge from compactifications on Calabi-Yau manifolds obtained as integrals over internal cycles of antisymmetric tensor fields, specifically Raymond potentials. Such actions like pseudo-scalar field Ix are defined as integrals over internal cycles sigma p. Alpha x is equal to integral the lower boundary sigma p CAP. The anti-symmetric properties of CAP endow these actions with intrinsic pseudo-scalar characteristics. We construct a cosmological toy model to capture action dynamic arising from the evolving Calabi-Yau geometries. Assuming a time-dependent volume modulus nullity, the action decay constant evolves as FIT is equal to m p1 divided by square root of nu t, and consequently the solar axion's mass varies as mr to the power of 2 t is equal to delta to the power of 2 qcd, which is a chorodynamic, a chromatic dynamic, and nuity divided by MAPI to the power of 2. The action's cosmological evolution is governed by the equation R plus 3HR plus MI to the power of 2TR is equal to 0, where the Hubble constant is equal to IT divided by IIT is the Hubble parameter. Starting from the effective 10-dimensional action, S is equal to 1 divided by 2 chi 10 to the power of 2 to integral d to the power of 10 x and square root minus g e to the power of minus 2 phi multiplied by r plus 4 delta phi to the power of 2 minus 1 divided by 2 absolute ff to the power of 2. The compactification on Calabi-Yau manifolds leads to the decomposition of the metric dA S10 to the power of 2 is equal to e to the power of 2 omega t g micro nu x dx to the power of micro dx to the power of nu plus e to the power of minus 2 omega t gmn y dy to the power of m dy to the power of n, with omega t describing internal geometry dynamics. The volume of the compactified space is nu t is equal to e to the power of minus 6 omega t. The modulus evolution is obtained from nu omega zegon plus 3 h omega prime is equal to minus delta V effective divided by delta omega, where V effective arises from fluxes and non-perturbative potential. Solving for omega t, we find Ft is equal to MPI divided by e to the power of minus 3 omega t. A solution close to the stabilization regime is approximated as omega t is equal to omega 0 plus delta omega e to the power of minus gamma Hubble constant t. Given explicitly, Ft is equal to F0 multiplied by 1 plus 3 delta omega e to the power of minus gamma Hubble t. The time-dependent nature of the action mass can induce parametric resonance phenomena describable by the Matthew equation after a suitable change of variables. The action equation of motion transforms into a form of the second derivative of I k divided by the second derivative of the z plus I k minus 2q cosinus 2z multiplied by alpha is equal to 0, where alpha and q are parameters dependent on the cosmological dynamics and action parameters. Alpha is equal to k to the power of 2 divided by alpha to the power of 2 h to the power of 2 plus m to the power of 2 divided by h to the power of 2. Q is equal to delta m out to the power of 2 divided by 2h to the power of 2, which delta m out to the power of 2 representing amplitude variations of the action mass. The Matthew equation is well known to possess stability and instability bands characterized by exponential growth resonance or stable oscillatory solutions depending on the values of I, k, and q. The resonance condition thus provides the enhanced production of action perturbations for certain wave modes, significantly modifying their observational signature in cosmological data such as gravitational waves and cosmic microwave background anisotropies. Parametric resonance resulting from Matthew dynamics leave distinct imprints on cosmological observable resonantly amplified action perturbations, contribute to observable gravitational wave signals, and influence the structure formation dynamics at various scales. Detections of such signatures in forthcoming gravitational wave experiments like LISA and pulsar timing arrays can provide direct evidence of string theoretic pseudo axioms and internal geometry dynamics during the early universe. So the actions decay into the gravitations and cosmological implications and gravitational wave signatures. The decay of the pseudo actions into gravitons provides a fascinating window into physics beyond the standard cosmological model, carrying rich observational consequences for gravitational wave astronomy. Actions initially proposed to resolve the strong CP problem can exhibit significant cosmological effects when coupling to gravity, potentially leaving distinct imprints in the gravitational wave background detectable by current and forthcoming observational facilities. Consider an axion field IX coupled directly to the gravitational fields via a parity violating interaction of the form that LAIRR is equal to alpha divided by 4IX multiplied by R micro rho sigma R prime to the power of micro nu rho sigma, where R micro nu rho sigma is the Riemann curvature tensor and R prime to the power of micro nu rho sigma is its dual. Such coupling generates action to gravity decay, producing observable gravitational waves, particularly during periods of rapid cosmological evolution, such as inflation or reheating. The effective action governing gravitational waves modified by axial decay can be represented as this equation: S is equal to integral the fourth derivative x square root minus g multiplied by mpi to the power of 2 divided by 2 r minus 1 divided by 2 delta micro r multiplied by delta micro r minus 1 divided by 2 m all to the power of 2 all to the power of 2 plus alpha divided by 4 r or a micronueve rho sigma r prime to the power of micronueve rho sigma, where MPI is the reduced Planck mass. The resulting modifier equations of the motion for tensor modes hij becomes hij plus alpha divided by m Planck mass to the power of 2 epsilon to the power of I car L delta car alpha delta L hj to the power of car is equal to 0. During these six cosmological epochs, so the action to gravitation conversion is dynamically amplified. Inflationary epoch. Rapid background evolution enhances the pseudo-axion's graviton coupling, potentially imprinting polarization asymmetries and spectral distortions in primordial gravitational waves. Now I want to talk about the two distinct and various these parameters as gravitational waves. Post-inflationary resonances, parametric resonance in axion dynamic amplifies gravitational wave production described effectively by Matthew equations, including sharp spectral peaks in gravitational wave backgrounds. And the next one is reheating and early matter era. Axion condensates form during inflation decay into gravitations, modifying standard predictions of stochastic gravitational wave background. Gravitational wave detectors, including ground-based observatories such as LIGO, Virgo, and Kogra, space-based interferometers, laser and pulsar timing arrays can potentially observe these distinctive gravitational wave signatures. The detection strategy relies on analyzing the gravitational wave stochastic background power spectrum omega GW or gravitational wave of a function is equal to 1 divided by rho c multiplied by dl rho gravitational wave divided by dl logarithm f, where rho c denotes the critical density and rho e gravitational waves energy density. Axion gravitation decay contributes unique polarization asymmetrics, facilitating clear identification among standard cosmological backgrounds. The pseudo-axion graviton decay represents a robust mechanism for probing alien universe physics through gravitational waves, providing distinct and observable predictions. Targeted observations from present and future gravitational wave detectors promise to offer unprecedented insight into axion physics parity violation in gravity and fundamental cosmological processes. Now I want to talk about the enhanced resonance decay of the pseudo-axions at specific cosmological epochs. Axion and pseudo-axions motivated by solving the strong CB problem and addressing cosmological parameter discrepancies, respectively, can undergo enhanced resonance decay into photons or gravitons during specific cosmological epochs. Such resonances arises due to parametric amplifications, a mechanism governed by the dynamically evolving background fields, moduli, and internal manifolds geometry. Understanding the precise resonance conditions and their observational implications requires a detailed mathematical and physical exploration. So the axions, in contrast to normal axions, have decay processes amplified by the flattening out of the pseudo cycles they originated from, bringing the new amplified signatures that can be observationally detected. The fundamental dynamics describing the pseudo axial resonance can be encapsulated in the Matthew type equations. The second derivative of alpha divided by z to the power of 2 plus alpha minus 2q cosinus 2z multiplied by alpha is equal to 0, where alpha is the pseudo-axial model amplitude and z represents a dimensionless time variable related to the cosmological time t by the z is equal to mit to the power of divided by 2. Here the Matthew parameters alpha and q are defined by the alpha is equal to 4 car to the power of 2 divided by m out to the power of 2 out to the power of 2 plus 2, and q is equal to 2 delta m out to the power of 2 divided by m out to the power of 2, where m is so the axiom mass delta m out to the power of 2 denotes the modulation amplitude of the mass square, and I is the cosmological scale factor. The resonance conditions emerge when alpha and q fall between the specific instability bands defined by the Matthew equations. Physically, these instability bands correspond to the parametric resonance regimes where pseudo-axion amplitudes grows exponentially due to the constructive interference effects in oscillatory modulation of their mass. This resonance amplification significantly enhances the decay rate into observable fields such as photons or gravitons. To characterize the resonance range and frequency, we numerically solve the Matthew equation using robust Rum-Kuta integration method solutions illustrate clear exponential growth phases bounded by characteristic stability regions. The numerical solutions presented in Figure 1 demonstrate the axion and mode evolution across a range of the resonance parameters. For example, taking representative cosmological parameters with q is equal to zero point 0.5 and alpha is equal to 2 yields a pronounced exponential growth regime followed by the saturation and null at nonlinear scales. So the axion resonance parameters depend sensitivity on cosmological epochs and modular stabilization scales. The modular derived dynamic dictates the evolution of the internal geometries and associated parameters, determining unique resonance conditions at distinct epochs. So you see the figure 1 is illustrating the pseudo-axial amplitude evolution with explicit nonlinear attenuation. The graph illustrates the pseudo-axial amplitude absolute alpha is the evolution governed by a modified Mathieu type equation incorporating nonlinear attenuation effects. Initially stable, the amplitude clearly enters a resonance region marked by the vertical dashed line at z is equal to 10 and z is equal to 35, exhibiting distinct exponential growths resulting from the parametric resonance. To ensure physical realism, nonlinear attenuation, introduced as a cubic damping term, was included, mimicking realistic back reaction and particle production mechanisms. This nonlinear term stabilizes the amplitude after the exponential growth, causing it to desaturate and preventing unphysical divergence. The balance oscillations before, during, and after resonance ensures a coherent physical interpretation, making these results particularly relevant for observational search of the pseudo axion signatures in cosmological scenarios. Table 1 describes resonance parameters for pseudo axion decay at specific cosmological epochs determined by moduli scales. Thank you so much for watching my tutorial video until the end. Today is the 19th day of the July 2026. Time is 10:30 in the morning.